Sure, guys. Hello. Welcome back to another video. Today we'll be talking about probabilities. So if I gave you the situation that we have a bag, didn't mean to do that. We have a bag with two blue balls and three red balls, and you had to pick one ball from the bag. And then once you look at it, you note it down and you put it back in. So with the replacement, you'll see this in some questions. You take it out with replacement, which is you put back what you took out, which is important for what we'll be looking at. So, okay, what's the probability of getting blue ball? Well, that's just simply the number of blue balls. That's two blue balls out of the entire number of balls. So it's 2/5, right? And the probability of getting a red ball is the number of red balls divided by the total. Okay, so it's essentially like out of this five, the only like three out of the five balls you can pick, the only three possibilities that get you a red ball. And out of the five balls you can pick, the only two possibilities that get you a blue ball. So the probability using like this kind of notation, instead of saying probability of, you can just write like P of event, just call that E of some event. So it could be like winning the lottery, getting free food, and then it's equal to whatever the probability is. Okay, so now I'm gonna ask a question. What's the probability of getting a blue ball and a red ball? Now, I mean like you pick one ball from. It sounds like a stupid question, right? You pick one. You only get to pick one ball from this. It can either be blue or red. It can't be both, right? Because I'm only picking one ball one time. And what's the probability of me getting a blue and a red ball? Well, there are no chances of me doing that. So it's a big fat zero. And that's essentially the situation we have in the in, sorry, mutually exclusive events. These events are mutually exclusive. They can happen on their own, but they can't happen together. You know what I mean? You can't pull out one ball and have it be in like a superposition of red and blue at the same time. You can only pick out a red ball or a blue ball. So that covers mutually exclusive events. Well, that sucks. Anyway, now we're gonna move on to independent. Independent. Actually, we could have looked at that itself, but anyway. Um, Imagine you're rolling a dice. I'll try and make my best dice. We all know what's on the dice. One. This is two. Let's say I literally don't know how to make a three on the dice. I assume they make it triangular. That's cool. And then you have a coin, and this is heads, and the bottom part is tails. So let's say I flip the coin. So these are sequence of events. Flip the coin, then roll the dice. Roll the dice. Flip the coin, then roll the dice. Okay. And I'm gonna look at the probability of me getting heads when I flip the coin, like on both flips, and the probability of me getting a 6 on each roll. Like getting a 6. Getting a 6. Yeah. So what's the probability of me getting heads over here when I first flip the coin? I mean, there's only one 6. What? What's the probability of me getting heads when I flip the coin? Okay, there's only one heads, and there are two possibilities, heads or tails. So it's a half. Okay, that's the probability of me getting heads. What's the probability of me getting 6? There's only one 6, and there's 6 faces. Now, when I flip the coin again, but just because I roll the dice, the probability of me flipping, of getting heads, has not changed, right? It hasn't changed at all. It's still 1 over 2. And conversely, the probability of me getting a 6 when I roll the dice again is still the same thing. It's still, even if I got tails here, this does not change. The probability of me rolling a 6 does not change. And these are called independent events. Their probabilities don't depend on the outcome of the other event. It doesn't matter if I get heads or tails here, it's still going to be 1 over 6. Doesn't matter if I get a 6 or a 5 or a 4 here, this is still going to be a half. Now, if you want to get like technical, because for mutually exclusive events, the probability of one event happening and the other event happening was equal to 0, right? So how would you represent that mathematically here, okay? So I'm just going to introduce something, and so the probability of getting, let's say heads is red, heads. Now this means given. Okay, let me just say roll 6. Given I roll a 6. So this kind of notation means the probability that this event happens given this event has happened. So essentially this event happened, so now what's the probability of this event happening? So for independent events, this is simply the same as saying, I mean, you can see it here, the probability of me getting heads here, given that I rolled a 6 here, is still the same as the probability of me, is just simply the same as me getting heads. Getting heads. It's exactly the same. And conversely, the probability of you rolling 6, given that you got heads, is still the same as the probability of you rolling a 6. And that's the condition for independent events. Now, of course, I don't think you need to know conditional probability yet, like this happening, but we'll still see. We'll see. I mean, it does seem like every event in life is going to be like this. Maybe if you just. But if we go back to the satchel and ball scenario, I'm switching up how many red balls and blue balls we have, I think. Now, I said with replacement, right? Which means that you take one out, you put it back. But what happens if you take one out and just take it out? Just take it out, man. So initially, the probability of getting a blue is equal to 3 over 5 in this case. It'd be really funny if 5 was not the total. Even though I'm the one who made this. Okay, but anyway, And then the probability of getting red is equal to 2 over 5. But now, if I'm not replacing and I take out a blue ball, right? And then I look at the probability of getting red. So now the probability of getting red, given blue, I took out a blue ball on this is on the first attempt. On the first taken out, has now changed because now without this blue ball inside here, there's still 2 red balls. I'll give you that. But now the total has changed. Now there are only 4 situations you have to look at. So the probability of getting red on the second time you take out a ball, given that you took out blue the first time, is not the same as just saying the probability of red. It's different. Now it's a half. You're more likely to get a red ball now. So this would be an example of like not in like I don't want to say dependent events because I never heard anyone say dependent events, but not independent events. Okay. Now let's look at different ways to represent probabilities. The satchel and thing is like so fun because so many things can happen. Okay, we're back here. We're back. Satchel looks more like a vase. We don't matter. It don't matter. Okay. So now let's look at it. So this is called a tree diagram because it branches out. Yeah, I'm pretty sure that's the only. It's like a sideways tree. Anyway, let's just start it. You'll get the gist of it. So what are the two possibilities? The two possibilities that can happen. The only two possibilities. We can pick a red or we can pick a blue. And now you have to write the probability on each arm, okay? It's 2/5 on each branch. 2 over 5. Okay. Sorry if that's not very visible. I'm trying to. Okay, 3 over 5 in this case. So let's make this tree diagram, but we're not replacing. So once we remove something, it's out. It's outie. So once we've removed the red, what's the probability of us getting a red again? Wow, this guy. Let's do this kind of. What's the probability of us getting a red again? Well, if we remove the red, then there's one less red, and there's one less ball from the entire thing. So the probability of us getting, let me just like make this clear that this is our node we're starting from here. Okay, we'll get there. So probability of us getting a red now is 1, because there's only one red ball once we've taken out one, and the total has gone down by 1, so it's 1 over 4. And the probability of us getting a blue ball now. Well, we didn't take out a blue ball before, so there's still 3 blue balls. But now there's one less ball. Like imagine if I took this out and asked you what the probability of getting a blue ball is now, is 3 over 4. Okay. And then if we come over here, the probability of us getting a red ball, there's still 2 red balls. We took out a blue ball. In this branch, we're imagining a world where we took out a blue ball. There's still 2 red balls, but now there are 4 balls left. And And if we look at here now, 3 minus 1, that's 2. And clearly it should be 50-50. I'll just go over why. It should be 50-50. Because all probabilities, the sum of probabilities should be equal to 1, right? On each like branch, like as I was saying, the sum of probabilities has to be equal to 1. Sorry about the degradation in quality in this like scene. Things happened, okay? Things happened. Anyway, it's equal to 1. So if you look at the sum of probabilities over here, 2 over 5 plus 3 over 5 is equal to 1. Over here, 1 over 4 plus 3 over 4, 4 over 4, 1. 2 over 4 plus 2 over 4, 4 over 4, 1. That's how you can check that you're correct. And that's how they can give you like funny questions where they say, oh, the probability over here is 1 over 10. Haha. What's the probability over here? Oh no, you don't know. But like, since the probabilities on since the sum probabilities on each branch, like I mean the sum probabilities, yeah, sum probabilities on each branch should equal 1. This clearly has to be like 9, not that kind of 9, but 9 over 10, right? Because those two add up to 10 over 10. Sorry about that. Anyway, yeah, you get the gist of it. So let's go to everyone's favorite topic, Venn diagrams. Get the tables. Venn diagrams. These will not be perfect circles. I admit that now. Great. So these guys are fun because you can kind of see the relationship between two events. So let's say A is the event. A is the event that, I don't know, Manchester United wins a game that night. Man U. Okay, Man U wins a game that night. And B is the event that what are some common events that can happen as Man U wins? B is the event that you'll be happy that day as an Arsenal fan. You'll be happy. You'll be happy that day. That's You'll be happy. Smile. So when you see two events overlapping, that initially tells you that these two events are not mutually exclusive. As in, they can happen together, they can happen at the same time. This means this intersection over here is essentially the probability of A. Now I'm going to use some set notation here. And B. Intersection essentially just means and, right? And then union, if you remember your symbols. And then union. Wait, what? Yeah, then union A, union B. means or. I Yeah, means or. Sorry, in terms of probability, like P of A or B happening. But we'll talk about that. We'll talk about this. This is special. This is something we should talk about. Anyway, coming back to it. So they usually like give you some percentages or like probabilities. So A of Man U winning is 0.1. All my betting bros know. A probability of A only happening. Sorry, this is probability of A only happening. Only A happening. Now the probability of B happening, let's say that's um say that's 0.5. It's a 50-50 chance. Now the probability of Man U winning and G being happy, well, we we can use like multiplication to get that. It's like, okay, you look at the probability of Man U winning, and then within the probability of Man U winning, what's the probability of you being happy? That's just gonna be like multiplied by the probability of you being happy. They both have to happen. That's just from probability. And that's, well, I'm just gonna write a fraction if I can. That's 1 over 20. 1 over 20. It's 1 over 20. And the probabilities, the sum of probabilities in this Venn diagram have to add up to 1. So 0.1 plus 0.5 plus 1 over 20. Right now, this all adds up to 0.65. So that means the rest of our solution space, I mean our probability space, sorry, has to have a probability of 0.35. So this 0.35 represents the probability of you being sad, of you not being happy, and the probability of Man U not winning. So this is the probability of Man U losing and you being sad. Because it's, so A complement, from set notation, A complement is Man U losing. Is Man U losing. So you have to look outside of that Man U Venn diagram, the A Venn diagram, right? So the probability of Man U, the two ways you can work it out. The probability of Man U winning is 0.1 plus that 1 over 20. That's 0.15. And then you can just, since all probabilities add up to 1, you can just say 1 minus the probability of Man United winning. So that gives you 0.85. That gives you 0.85. And anyone who's good at mental maths can also see that you can just add up the probabilities outside of the circle. So 0.5 plus 0.35 gets you back to 0.85. And then the probability, and yeah, same thing with B complement, which is the probability of you being sad. You just add up everything else here. So that's 0.1 plus 0.35, which is 0.45. Okay. Now, if we come to just using A union B to get or, like A happening or happening, let's just work it out initially from the Venn diagram. Let's look at the Venn diagram. What's the probability of A or B happening? I mean, you just have to add up these. So it's 0.1 plus 1 over 20 plus 0.5. It's 0.65, okay? The probability of Man U winning or you being happy is just 0.65. Now, how would you calculate A union B? I mean, you'd essentially just look at A, that's 0.1 plus 1 over 20. And you would add on b, right? So that's, and b, if you look at b itself, that's 0.5 plus 1 over 20. But now there's an issue here, because we're counting that 1 over 20 twice. So this union just means add up all the percentages, the probabilities in A. Take the probabilities from A of A happening, that's 0.1 plus 1 over 20, and then add it to the probability of B happening, which is 1 over 20 plus 0.5, right? But now you count this intersection twice. So the proper way to get OR from a Venn diagram is P of A union B minus P of A intersection B. Because if you just take A union B, you're counting this 1 over 20 twice. So if we look at it again, the probability, so I'm just trying to take it back to where, because in this case it's clear that you just add up these three numbers, you don't overcount. But sometimes they can tell you, let's say they told you the probability of A was equal, because the 0.1 is not the probability of A. The 0.1 is the probability of A only happening. The probability of A happening is A happening by itself, and also when A happens with B. So that's 0.1 plus 1 over 20. So the probability of A happening is 0.15. And then the probability of B happening is 0.55, right? And now imagine they told you, and in this case they have to tell you the probability of A and B happening, because that's because multiplying these together, because since A and B are not mutually exclusive, the probability of A and B happening is already kind of baked into the probability of B and A, right? So you can't just say the probability of A and B happening is 0.15 times 0.55, because that's just a whole different kind of wrong in this case. So the probability of A and B happening, they'll give it to you. This is going to be given, is equal to 1 over 20, right? So now they ask you, what's the probability of A or B happening, right? So in any case where the events are mutually exclusive, as in they can't happen at the same time, having one of them happen. So like if you take it back to the situation where you have a bag filled with reds and blues, and you think about on your first turn, so it doesn't matter if I say replacement or no replacement, just you're taking out one ball. The probability of you getting a red ball could be, let's say, 2 out of 5. And the probability of you getting a blue ball is 3 over 5. But since these events are mutually exclusive, the probability of you getting a red ball or a blue ball is simply 3 over 5 plus 2 over 5, which is 1. You won't, since they're only red balls and blue balls, you are guaranteed to get a red ball or a blue ball. So you see, I don't have to subtract the probability of them happening together, because remember, in mutually exclusive events,
P of A and B is equal to 0, right? You can't pull a red ball and a blue ball. So in that case, when I say or, I just add the probabilities and I don't subtract anything because they can't happen at the same time. But in this case, Man U can win and you can be happy, right? They are not mutually exclusive. So I can't just add their probabilities to get A or B, right? Because there'll be that overlap I have to account for. So if I want to get, if they just gave you figures. They didn't give you a nice Venn diagram with things with things already added. So if I say 0.15 plus 0.55, that's 0.7. And we know that's wrong. That's not the probability of A or B happening. You have to subtract that 1 over 20 that they give you. And that gives you 0.65, which is our correct answer. Okay, great. I think we pick this up again another time because I feel like this video is getting long.